Good evening. I will wait for 2 minutes and I will start. Then I will start. Give me a minute. I am facing some problems, so So we will start now. Sorry for the delay. So we are in week 7 now, and we will solve the problems regarding this week 7 lecture that have been taught by Professor Sandeep Paul. So we will start, and first we will start with basic concept. So am I audible? Please write in message box. So we will start with this vibrational partition function now. So vibrational partition function. QAB. So vibration partition function we have calculated in the class as well. Sir already did the expressions. So I'll just write the formula and we will just solve the problem regarding this. So QV is equals to E to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. This is the normal, this is normally the Q vibrational without any approximation. So how do we calculate this? I'll just quickly show. So it can be calculated as we know. Q is the summation of all the e to the power minus ei by kBt all. And we know that in harmonic oscillator, energy levels are equispaced. So this is the zero energy. So we know E energy is equals to n plus half h nu. We know this. So for ground state energy, for nu is equals to 0. This is the ground state energy. E naught is equals to half h nu. Okay, and so on, like E1 is equals to 3 by 2 h nu, E2 is equals to 5 by 2 h nu. We know this. So now we can write it as e to the power minus h nu by 2 kBt plus e to the power minus h nu by 3 by 2 kBt plus e to the power minus 5 by 2 h nu by kBt and so on. So by taking e to the power minus h nu by 2 kB 2 kBt as the common, and we will be left by e to the power h nu by kBt divided by this. So this will be half e to the power minus h nu by kBt plus e to the power minus, so this will be minus 1 2. Okay, so this is half, so minus half, so 5 by 2 minus half, this will be 4 by 2 h nu by kBt, and so on. So now if we write it as 1 plus e to the power minus x, then it will become e to the power minus 2x, and so on, e to the power minus 3x, so on. So how can we solve it now? This will be equal to 1 plus e to the power minus x, plus we can write it as e to the power minus x square, since we know the power can be multiplied, so this can be written as like this. So e to the power minus x cube, and so on. If we say e to the power minus x is equals to y, then this equation will become 1 plus y square plus y cube, and so on. So let me go to the next page. So this has become 1 plus y square plus y cube, and we know this is just the Taylor expansion of 1 over 1 minus y. Taylor expansion of 1 over 1 minus y is 1 plus y square plus y cube, and so on. So this we have gotten. So, and we know y is e to the power minus x, and x is h nu by kBt. So this will become what we got from here, q vibrational is equal to e to the power minus 2 h nu by e to the power to h nu by 2 kBt, h nu by 2 kBt, and here this is 1 over 1 minus y is e to the power minus x, e to the power minus x is e to the power h nu, e to the power minus h nu by kBt. So this is the formula, e to the power minus h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. So this is the formula for q vibrational. Now let's say if we take this ground state energy as 0, ground state energy if we take it as 0, then all the function will be, the energy difference is h nu between the two states, so this will become 0, h nu, 2h nu, 3h nu, and so on. So EV will be, let's say it is EV dash will be an h nu. Okay, so let's solve this. Then q is q vibrational dash, let's say it is q vibrational dash. Q vibration dash will be summation of e to the power minus ei by kBt. So again we will expand this. This will be summation, e to the power, then at ground level it will be e to the power 0, so it is 1, e to the power minus h nu by kBt plus e to the power minus 2h nu by kBt, and so on. So now q dash vibrational is equals to, at 0 point energy E naught is equals to 0. Okay, so this is equals to 1 plus e to the power minus h nu by kBt Give me a minute. Laser pointer is not working. Give me a minute. Okay, so where were we? We were like Q vibrational dash is equals to 1 plus e to the power minus h nu by kBt plus e to the power minus 2h nu by kBt plus e to the power minus 3h nu by kBt, and like we did in previous one, we can say that this is 1 plus e to the power h nu by kBt plus e to the power minus h nu by kBt square plus e to the power minus 2h nu, 3h nu, so okay 2h nu by kBt to the power 3 and so on. So this we can write it as e to the power minus x, e to the power minus x square, minus was outside, it was outside, e to the power minus x cube and so on. We can write it as 1 plus y square plus y cube and so on. So this is 1 over 1 minus I y. So we can write it as 1 over 1 minus e to the power minus h nu by kBt when ground state energy E naught is equals to 0. I hope it is clear to you now. Now let's solve it for high temperature and low temperature. So Q vibrational normal when E0 is equals to half h nu. So this is e to the power minus h nu by 2 kBt divided by e to the 1 minus e to the power minus h nu by kBt. If we say that h nu by kB is equals to theta, this will have a unit of temperature. So we call it as vibrational characteristic vibrational temperature. So we can write it as e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. So this is the formula. Now for low temperature, low, what will happen? Temperature is low, theta by t will be very greater than 1. Then e to the power minus theta by t will be very greater than 1, because as this is the minus, so this will become 1 over e to the power theta by t. So as this quantity increases, this whole quantity increase and this whole quantity will decrease. So this is very less than, sorry. So this is less than 1. Okay. Now, as this is very less than 1, we can say e to the power minus theta very less than 1. So this will become 1 minus e to the power minus theta by t will be approximately equal to 1. So Q vibrational will become at low temperature, Q vibrational will become e to the power minus theta by 2t. At high temperature, what will happen at high temperature? Now theta by t is very less than 1, because t is more, then theta by t will be very less than 1. Now e to the power minus theta by t, how we calculate this? If we expand this according to the Taylor series, this will be 1 minus theta by t plus theta by t square divided by 2 factorial plus 1 by 3 factorial theta by t whole cube. So this is when we expand this. So we know that theta by t is very less than 1. So we can, if we square this quantity will become even more like negligible. So we can neglect about this third term. So from second term onward we can neglect the values. So this will become 1 minus theta by t. So at high temperature, e to the power theta by t minus theta by t will become 1 minus theta by t. So the Q vibrational is e to the power minus theta by 2t divided by 1 minus e to the power theta by t. So the problem is solving this this denominator part. So we have applied this here. So this has become 1 minus 1 plus theta by t. So this will cancel out. So it will become t by theta e to the power minus theta by 2t. So this is Q vibrational. So we can always ask why we have not applied this to this part. This is in multiplication, so it will not affect that much. So we only are making change into this denominator part. Okay. So this was all about vibrational partition function. We can revise other two partition function as well, so that we can solve the questions. So other two are, since we know that Q total is equal to Q electronic into Q vibrational, Q rotational and Q translational. So Q translational partition function for translational motion is two pi m kBt divided by h square to the power 3 by 2 into volume. We can write it as V by lambda cube. This lambda is the de Broglie wavelength. So this is the Q translational. So we can say that this lambda is equals to what will be the lambda? H over this is Q. So H over under root 2 pi m kVt. So this is the de Broglie wavelength, and this is the translational partition function. Now to the next, rotational. Partition function. Q rotational is equals to kVt by sigma HCB. So what is sigma here? Sigma is symmetry factor. And its value will be either 1 or 2. For heterodiatomic, the value is 1, and for homodiatomic molecule, the value is 2, such as H2, N2, etc. Here CO, NO, etc. or CN. We can write it as T over sigma theta. So, and what is the B here? B is H over 8 pi square IC, rotational constant. So now theta is equals to B HCB by kb. So if we put B here, this will be H square theta is equal to HCB by kb, and then theta will be HCB by kb. B is H square C by 8 pi square IC, and if we put the whole value in Q rotational, this will be kBt divided by sigma H square C 8 pi square IC. C will cancel out, so this will be 8 pi square I kBt divided by sigma H square. So we will calculate, somewhere we will calculate this value of average value of Kp. Then this will be Kt ln, sorry, curl by curl V of ln Q at constant temperature. So this is very important formula. Other important formula is this internal energy U, or you can say it is E. This is equals to N kVt square. This is also N for N number of molecules. But this is average, so that's why we have not put N here. So kVt, this is kV. So this is kV, N kVt square curl by curl T of ln Q at constant volume. So this is internal energy, and we know that we can calculate this Helmholtz A also, which is equal to U minus Ts, and S, it will have the value N kVt sorry, n kb ln q plus u by t for distinguishable, and for indistinguishable this will be n kb ln q by n plus u by t plus n kb. Okay, by putting this value we can calculate this A. Similarly, G is equals to H minus Ts and H is equals to U plus PV. U plus PV minus Ts will give G. So we know G, U, we know S. By putting the values we can get the G. So like this we can always calculate thermodynamic functions. So thermodynamic properties and functions can be calculated by using partition function Q. So now we will start the question part. I think, okay, I'll quickly tell one more thing about this partition functions. There are mainly, which we study, there are mainly three type of ensembles. One is micro-canonical, one is canonical, and one is grand canonical. So, what is the difference between these three? So, micro-canonical will have number of particles, volume and energy constant. So, if there are many partitions, these are the partitions 1, 2, 3, 4, like 1, 2, 3, 4, 5, 6, 7, so many. So what will be the property of microcanonical? This all 1, 2, 3, 4, this will have number of particles constant, all will have same number of particles, volume will be constant and energy will be constant in these partition functions. In canonical, NVT means number of particles, volume and temperature will be constant. And in grand canonical, chemical potential, volume and temperature is constant. Among these partitions, these are the partitions. And each of these partition is defined by this Q partition function and these thermodynamic properties. So let's start the question part now. So this is the first question. This is from assignment. Q is given. Calculate the average pressure of the system. So average pressure P is equals to kBT curl by curl V of ln Q at constant temperature. Okay. So Q is given. Q is equals to exponential of A cube T to the power 3 by 2 V cube. Ln Q will be A cube T to the power 3 by 2 V cube. Okay, we need curl by curl V of ln Q at constant temperature. So it will be A is also a constant. So it will be A cube T to the power 3 by 2 into 3 V square. Power will come ahead and then 1 will subtract from 3. So this will be 3 V square. So this is 3A cube T to the power 3 by 2 V square. is some problem. I don't know where is the problem. Give me a minute. It is okay now. Again, I am not able to present. Okay, so we were solving this. So we get this value of ln q is equals to a cube 3 to the power 3 by t to the power 3 by 2 v cube, and then this curl ln q by curl v is equals to a cube at constant temperature is equals to 3 by 2 into 3 v square. Now we know this u is equals to kb t square into a cube t to the power 3 by 2 into 3 v square, that is equals to 3 kb a square t to the power 3 plus 5 by 2 into v square. So this is the value of u. Okay, sorry, but we are not calculating u, we are calculating this average pressure. So P is equals to kBT L curl by, sorry, this is not u will be with respect to T. So sorry, P is equals to kBT curl by curl V of ln Q at constant temperature. So this will become kB T into a cube t to the power 3 by 2 into 3 v square. So this will be 3 kb aq t to the power 1 plus 3 by 2, this is equal to 5 by 2 v square. So this is the answer. Average value of P is 3 kb aq t to the power 5 by 2 into v square. This option is not here, but I think whatever we have done, it is correct. So maybe the options are not correct. So I assume that, let's say this is 3, and then I think it is matching now. So this will be the option. I will check it with the team which is uploading these questions. So after that I will confirm this in the next class. But as we have done all correct thing, kBT curl by curl V of ln Q at constant temperature. So it will only give 3 only in front of this. Only 3 will come. So I will check this, and in the next class I will again solve this problem. Okay. Now, in the classical microcanonical ensemble for a system of n interacting particles, the fundamental volume in phase, which is regarded as the equivalent to 1 microstate. Okay. So they are saying that there are n interacting particle in an ensemble. Like, let's say this is one ensemble, cubic. Let's say this is cubic box of n particles into it. What will be the volume in the phase? So it will be, so there are n particles, that means there are 3n degree of freedom. So each particle can interact with any particle, and it has 3n degree of freedom. So its volume will be, phase volume will be h to the power 3n. So this is the answer. In grand canonical ensemble, a system A of a fixed volume is in contact with a large reservoir B. A is in connection with a large reservoir B. System A and system B. Then A can exchange neither energy nor particle. So it is saying that energy E, delta E not constant, not equal to 0, and delta n not equal to 0, first part. Then it is saying, okay, they are asking about grand canonical ensemble. So we know that in grand canonical, mu, v and t are constant. That means delta mu is equals to 0, delta v is equals to 0, and delta t is equals to 0. Okay. The second option, A can exchange both energy and particle with B. Okay. Sorry. A can exchange both energy and particle. Okay. That means delta n not equal to 0, delta E not equal to 0. Okay. Third one, A can exchange only energy, delta E is equal to 0, not equal to 0, and delta n is equal to 0. So what A can exchange? Neither. Okay. So this is delta E is constant and delta n is constant. Then delta n and delta E both are not constant. And then in fourth part, A can exchange only particles. So delta n is not equal to 0, delta E is equal to 0. But if we see here, only mu, v, t are constant. That means n and E are not constant. For an grand canonical ensemble, n and E are not constant. So n and E are not constant, that means this is the option. The second one, A can exchange both energy and particle with B. What it cannot exchange, the volume change should be 0, temperature change should be 0, and change in chemical potential should be 0. Apart from that, this temperature and this apart from these three quantities, other quantity are not constant. So these two are not constant. So A can exchange both energy and particle with B. So option B. What is the fraction of O2 molecule in V is equals to 0 and nu is equal to 0 and nu is equal to 1 vibrational state at 383 Kelvin? Theta vibrational is given. This is the theta vibrational. So given quantities are theta vibrational is equal to 3683 Kelvin. Temperature is equals to 383 Kelvin. And we know Q vibrational is equals to e to the power minus theta by 2t divided by e to the power minus theta by t 1 minus plus 1 minus e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. So first we will calculate theta by t. Theta by t is equals to 3683 divided by 383. So let's quickly calculate it by using calculator. 3683 divided by 383. This is 9.616. So now putting the values here, this will be e to the power minus 9.616 divided by 2, 1 minus e to the power minus 9.616. Okay. So minus 9.616 exponential is minus 9.616 divided by 2. This is 4.8 and its exponential is equals to what is the fraction of, okay, they are asking for fraction of O2. Sorry, they are not asking for Q vibrational, they are asking for fraction of O2 in nu 0 and nu 1. So they are asking about N1 by N naught, and we know that N1 by N naught is equal to e to the power E1 by kBt divided by e to the power minus E naught by kBt. So we know that E nu is equal to nu plus half h nu. So it will be e to the power minus, then for E0 this is equal to half h nu, and E1 it will be 3 by 2 h nu. So okay, e to the power minus 3 by 2 h nu by kBt divided by, this is the fraction of O2 molecule in V0 and V. Okay. E to the power minus h nu by 2 kBt. So this will be e to the power minus 3 by 2 theta by t. This is e to the power minus theta by 2t. So this is equals to e to the power minus 3 by 2 plus half theta by t. So this is e to the power minus theta by t. So we know theta by t is equals to 9.616. So e to the power minus theta by t is equal to e to the power minus 9.616. So this will be the answer, and we will calculate it by using calculator. 9.616 exponential. This is 6.6 into 10 to the power minus 5. This value is equals to 6.6 into 10 to the power minus 5. So this is the answer. 6.6. Okay, this is the answer. 6.6 into 10 to the power minus 5. Okay, we will solve this question, then we will take a break. The value of molecular partition function of CO for rotation at 4200 Kelvin is this. QR is given 16.04 and theta r is what? They want to know this. Temperature is 4200 Kelvin and we know QR is equal to kBT, T by sigma theta r. And for CO, this is heteroatomic gas, so heterodiatomic gas, sigma is equals to 1. So QR will become T by theta r. And since both quantities are okay, QR and temperature are given, we can calculate theta r is equal to 4200 by QR, that is equal to 42 in Kelvin, 00 divided by 16.04. This will be 4200 divided by 16.04 is equals to 261.84. 261.85. So this is the answer. Okay, let's solve this question and then we'll take it. Okay. What is the fraction of N2 molecule in nu is equals to 0 and nu is equals to 1 vibrational state at this temperature when theta vibrational is given? We have done similar question here. Fraction of N2 molecule in nu is equal to 0 and nu is equal to 1 state, that is N1 by N naught is equals to e to the power minus E1 by kBT divided by e to the power minus E naught by kBT. That is equals to e to the power minus, since we know that E1 is equals to 3 by 2 h nu and E naught is equals to half h nu. So this is 3 by 2 h nu by kBT divided by e to the power minus half h nu by kBT. So this is equals to e to the power if we subtract it here, this will be minus 3 by 2 plus half, and then this will be this is e to the power minus h nu by kBT, and since we know that theta r is equals to theta v is equals to h nu by kb, then this will be e to the power minus theta by t and 1 by n naught. So all the values are given. So this is equals to e to the power minus theta is 3240 Kelvin and temperature is 453 Kelvin. So this will be e to the power, let's calculate this directly, 3240 divided by 453 and minus taking exponential, this is 7.8 into 2, 3, 4, 5, 10 to the power minus 5. Okay, 7.8 into 10 to the power minus 5, or we can say 0.78 into 10 to the power minus 4. So this is the answer. So I'll be back in 2 minutes. Okay, so let's start again. To the next question. All good. So now the fundamental vibrational frequency of F2 is given. Calculate the vibrational partition function of F2 at temperature 25 degrees Celsius. So what is given? The nu is given 2.676 into 10 to the power 13 Hz. Okay. So we know this is per second only, and we need to calculate vibrational partition function, Q vibrational. So it is not defined that we are taking 0 point energy or not, so we can calculate it for 0 point energy as well. So fundamental vibration is given. Okay, let's calculate it with full formula. E to the power minus theta by 2t, e to 1 minus e to the power minus theta by t. So first we will calculate theta by t, and then just put value, by putting the value here we can get the answer. So this is in per second. So we know that this energy is equals to h nu, half h nu for half h nu, then this and so on. Sorry, nu plus half h nu. You can say it like this only. E nu is equal to this. So, and the gap between the respective states is h nu. And we know theta is equals to h nu by kb. So first we will calculate this theta. Theta is equals to h nu. H is 6.626 into 10 to the power minus 34 joule second into nu is given 2.676 into 10 to the power 13 per second divided by kb is 1.38 into 10 to the power minus 23 joule per Kelvin. So joule will cancel out, per second will cancel out. So this will be in Kelvin. Theta is in Kelvin, something into Kelvin. Okay. So just quickly calculate the powers. 23, then it will become 10 to the power plus 23 on numerator. So this is 20. 36, and then this is minus, so this is 10 to the power 2, and rest we will quickly calculate. 6.626 into 2.676 divided by 1.38, this is equals to 1 to 12.8486. So we can say this is 1284.86 Kelvin. So theta is this, and then theta by t is 1284.86 divided by temperature is 298. So we will calculate this quickly. Into 100 divided by 298. This is 4.312 theta by t. Okay. Quickly we can calculate it, the others value as well. So now Q vibrational is equals to e to the power minus 4.312 by 2 divided by 1 minus e to the power minus 4.312. Simply putting the values. So taking the exponential of it, so this is 0.115 divided by 1 minus 4.312 exponential, this is 0.0134. Okay, so minus 1, this is 0.115 divided by 0.98, this will be 0.0134 divided by 0.98, so this will become 0.0134 Okay, again 0.115 divided by 0.98 is equals to 0.117. 0.117. So this is the answer to this question. To the next question now. Vibrational energy levels of iodine vapor occur at the following wave numbers above the 0 point energy level. This and this above the 0 point energy level. Calculate the vibrational partition function of iodine at 27 degrees Celsius. So let's calculate the difference between all. So we need to know either whether this is harmonic or anharmonic. So 636.27 minus 213.3, this is equals to, difference between these two is 422.97, and between 0 point energy and this is this. Okay, so 845.93 minus 636.27 is equals to 209. This is 209. Okay, this is not an harmonic one, so we can simply apply this formula. Q is equals to summation of e to exponential of minus ei by kVt. And let's say 0 point energy is 0. Nu is equal to 0, energy is equals to 0. So then this is equals to 213.30, and then this will become 636.27 and so on, all these values. So this will be nu1 for nu1, this will for nu2, sorry, E1, E2, E3, E4 and so on. E0 is equal to 0. So Q will be e to the power 0 plus e to the power minus E1 by kVt plus e to the power minus E2 by kVt. How many are there? 1, 2, 3, 4 and 1 ground state. E to the power minus E3 by kVt, e to the power minus E4 by kVt. Okay. Since the energy is given in per centimeter, so we need to calculate it in let's calculate kVt in per centimeter. kVt. So this is 1.38 into 10 to the power minus 23 joule per Kelvin into temperature is given 27. So this is 300 Kelvin. So this is in joule. Quickly calculate this. 1.38 into 300, 414. 414 into 10 to the power minus 23 joule. So now we need to convert into per centimeter. So we know that energy is Hc upon lambda. So this lambda is 1 over lambda is per centimeter. If we multiply it with H and C, we will get the answer in per centimeter. kVt is Hc upon lambda. Okay, divide by this Hc. This is equal to Hc upon lambda, and then this will be 1 over. Okay, so if we divide this kVt by Hc, we will get in per centimeter. Okay, so this will be 414 into 10 to the power minus 23 divided by H, 6.626 into 10 to the power minus 34 joule second into, this is joule, into 3 into 10 to the power minus 10 per centimeter. So this will cancel out. this was in joule only, this joule second, okay, my mistake, centimeter per second. This is speed of light, 3 into 10 to the power minus 10 centimeter per second. This second will cancel out, so this will be per centimeter whole. So this all term will be per centimeter. So quickly we can calculate the value. So this is again not working. Okay, I'll note these values and again I will solve this. KBT is equals to 414 into 10 to the power minus 23. Okay. Divided by HC. So where were we? Sorry for this interruption. So KBT is equals to 414 into 10 to the power minus 23 joule. Okay, so we were converting it into by dividing it at C and converting it into per centimeter. This all. So this will be 414 into 10 to the power minus 23 divided by 6.626 into 10 to the power minus 34 and into 3 into 10 to the power minus 10. So this will become, calculate this, 414 divided by 6.626 and 3, this is 20.82 into 10 to the power, this is plus 3 into 10 to the power plus 10. So this is 24 minus 24 and then this will be 10 only. So this is 208.2 in per centimeter KBT. This is the value of KBT, and Q the value of Q was 1 plus e to the power, if we start with 0 point energy, then for first state this was, now we have converted it into per centimeter, so we can put energy in per centimeter also. So this is 213.3 divided by 208.2 plus e to the power minus 636.27 divided by 208.2, then plus e to the power minus 845.93 divided by 208.92 plus e to the power minus 1054.38 divided by 208.2. This is 2 only. So we can calculate these values. Okay, 213.3 divided by 208.2 is equals to this, and taking the exponential, this is 1 plus 0.3589 plus 636.27 divided by 208.2. This is 0.0470 minus 845.93 divided by 208.2 and exponential. This is 0.0172 minus 1054.38 divided by 208.2 and exponential. This is 0.0063. So by adding this 0.047 1 plus 0.3589 plus 0.0471 plus 0.0172 plus 0.0063. This value is 1.4295. So Q is 1.4295 at 27 degrees Celsius. So now to the next question. If you have any doubt, you can ask now. Otherwise, I will move to the next question. So next question is calculate the relative Boltzmann population of iodine molecule in the ground first and second excited vibrational energy levels. And vibrational frequency of iodine is given. So nu is given 214.6 per centimeter. I have to check this, whether it is 0.6 or 6. So it is, I guess it is 6 or 0.6 only. So let's solve with 0.6. Don't have this question now. Okay, this is 0.6 only. So again this nu is given and we need to calculate the relative Boltzmann populations of iodine molecule in the ground excited and second excited states. So this is ground first excited and second excited state, and we know that this they are asking for this relative. So we know that N0 divided by, in relation to other all the quantity, this will be N0 plus N1 plus N2. So the relative population of N0 will be N0 divided by N0 plus N1 plus N2, and for N1 this will be N1 divided by N0 plus N1 plus N2, and for second excited state this will be N0 plus N2 divided by N0 plus N1 plus N2. So these three quantity we need to calculate, this and this, and we know that N0 plus N1 plus N2 can be written as a to the power minus E1 by E0 by kBt E1 by kVt plus E2 by kVt. And we also know that energy E is equals to nu plus half h nu. This is quantum vibrational number, and V is equal to 0, 1, 2 and so on. This is vibrational number. Vibrational state it is representing, whether it is in ground, first, second or third. So then this E naught will be half h nu, E1 will be 3 by 2 h nu, and E2 is 5 by 2 h nu. So we can put these values here. So this will be e to the power minus h nu by 2 kVt plus e to the power minus h nu by 3 by 2 kVt e to the power minus 5 by 2 h nu by kVt. So again this nu is given in this per centimeter. So now again we can calculate this kVt in per centimeter, but this time temperature is 25 degrees. So kVt is equal to K 1.38 into 10 to the power minus 23, joule per Kelvin into 298 Kelvin. So this is in joule, and divide it by h 6.626 into 10 to the power minus 34 joule second into 3 into 10 to the power minus 10 centimeter per second. So this will become in per centimeter. So let's calculate this. 298 into 1.38 divided by 6.626 and 3, and this all unit, this will be 206.88 per centimeter. So now we can put these values here, and we know this h nu. Okay. H we could have h nu. Now okay, now we do not need this h. We can simply put this per centimeter and this per centimeter. So this will only be n naught plus n1 plus n2 is equals to e to the power minus, this is 214.6 divided by 206.88, and since this is 2, so this will be 2 here into 2 plus e to the power 3 by 2 minus into 214.6 divided by 206.88 plus e to the power minus 5 by 2 into 214.6 divided by 206.88. So this one quantity is common in all, so we can first calculate this and then put these values in all the respective one. So first I will erase this. Okay, now this n naught plus n1 plus n2 is equals to, quickly we can calculate these values. 214.6 divided by 206.88 divided by 2, e to the power minus 0.5186 plus e to the power, multiply it with 3, this is minus 1.56 plus e to the power (2.59). So this is the n naught plus n1 plus n2. So this is the n naught, n1 and n2. So n naught divided by n1 plus n2 plus n3 can be calculated from here. So this is this quantity is equals to 0.0745. This is 0.21. This is 0.595. Okay, now put it here. 0.595 divided by 0.595 plus 0.21 plus 0.075. This is for first ground state, and now n1 divided by n1 plus n2 plus n3 is equals to, we can solve this. This is 0.88, and for n1 this is 0.21, for n2 this is 0.075, and this is 0.88. So 0.595 divided by 0.88 is equals to 0.676. This is equals to 0.238, and this is equals to 0.085. So we can notice one thing, that the relative population from ground state to the first excited state and then the second, the ground state has the maximum relative population, and then this first excited state, and then this second excited state has very less value. And when we add all these quantity, this will be very close to 1. That means the other vibrational levels that are above these 2 states, 3 states, they will have only very less amount of the particles, molecules in their excited state. So mostly they are found in this ground level. So these are the answer for ground, first and second excited state. So now we will move to the next question. If you have any doubt, you can ask. For H2 gas at 3000 Kelvin, calculate the characteristic vibrational temperature theta V, and the vibrational partition function q vibrational, given that the fundamental vibrational frequency of H2 molecules obtained from Raman spectra is this. Okay, again this nu is given 4405.3 per centimeter. We need to calculate theta V, and temperature is given. Again it is not working. So this is the pointer. Pointer is working but pen is not working. How and why? So the given quantity is nu 4405.3, and theta nu we need to calculate. Temperature is given. Okay, and we know q vibrational is equals to we need to calculate two things. One is q vibrational and other is theta v. Okay. And we know that theta vibrational is nothing but the h nu by kb, and q vibrational is e to the power minus theta by t 2t divided by 1 minus e to the power minus theta by t. So first we will calculate theta and then put here. Theta is equals to h nu by kb. Nu is in per centimeter, so we need to take care the units as well. So h nu divided by hc will give us what unit? H is in, so h will cancel out h, so nu is in, if it is in per second per centimeter, then this will be in centimeter per second. Okay, give me a minute. We will use the that we have solved before. We will again solve it like that only. So theta is equals to h nu. H nu, we need to calculate this first from this, and then we'll divide it by kb, and theta v will be in Kelvin. So we can write it as hc by lambda into kb. So this is 6.626 into 10 to the power minus 34. C is 3 into 10 to the power 10 centimeter per second. Okay. Okay. I don't know what is happening. Now it is black. Whew. So theta is equals to h nu by kbt, h nu by kb, and h is 6.626 into 10 to the power minus 34 joule second. Nu is 3 into 10 to the power minus, nu is equal to C by 1 lambda, so this is 3 into 10 to the power minus 10 per centimeter into 4405.3 per centimeter, centimeter per second, and this second will cancel out, this per centimeter will cancel out, and then there is kb 1.38 into 10 to the power minus 23 joule per Kelvin, and this joule will cancel out, so this will be in Kelvin. So cancelling the powers, 10 to the power minus 24, again this is plus, C is 3 into 10 to the power 10 centimeter per second, this is speed of light. So this is 24 and then this is 10 to the power minus 1, and this is 6.626 into 3 into 4405.3 divided by 1.38. Can calculate it quickly. 6.626 into 3 into 4405.3 divided by 1.38. This is, I think I have made some, again I will calculate this. 6.626 into 3 into 4405.3 divided by 1.38 divided by 10. So this is 6345.55 Kelvin. This is theta V, characteristic vibrational temperature. And we know that Q vibrational is equals to e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. So this is e to the power minus theta by temperature is 3000 into 2, this is 2 into 1 minus e to the power minus 6345.55 divided by 3000, that is equals to 1 minus e to the power minus 2.11 and e to the power minus 1.06. So this is equals to 0.35 divided by 0.88. So this is equals to 0.4. This is the Q vibration. I think the calculate the and let's say if we calculate it for the this Q dash vibrational, then what will be the answer? 1 over 1 minus this is for 0 point energy is equal to 0, E0 is equal to 0. Then how will we get the answer? This will be 1 over 0.88, that is equals to 1 1 divided by 0.88, so this is 1.13. So you can see that there is a lot of difference in these two values at 0 point energy and then at normal, so there is a difference. Now we will move to the next question, and the energy level of harmonic oscillator are E nu is equal to NH nu, assuming H nu is equal to kBt. H nu is equal to kBt given, and E nu is equal to NH nu, that is meaning of this is that this is 0 point energy is equal to 0. They are taking it as 0. So partition function Q is for this 1 over 1 minus e to the power minus theta by t, that is equal to 1 over 1 minus e to the power minus h nu by kBt, and they have said that h nu is equal to kBt, so this is 1 over 1 minus e to the power minus kBt divided by kBt, so this is 1 over 1 minus e to the power minus 1. So which one is the option? 1 over 1 minus 1 upon e, 1 over 1 minus 1 upon e. Okay, this is the answer. The low and high temperature limit of vibration partition function are given by. So I have solved it in my introduction part as well. So I will solve it again. Q vibrational is equals to e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t at low temperature t. Theta by t is very greater than 1 because t is in denominator, implies e to the power minus theta by t at low temperature. This is very greater than 1. That means e to the power minus theta by t is very less than 1, and hence we can neglect this quantity. So this will become Q vibrational is equals to e to the power minus theta by 2t only at low temperature. So at low temperature Q vibrational is equals to e to the power minus theta by 2t. Okay. At high temperature Q vibrational, we know that Q vibrational is equals to, for normal, minus theta by 2t e to the power 1 minus e to the power minus theta by t. So at high temperature theta by t will be very less than 1. So now we cannot neglect this part. So we have to solve this part. So we know e to the power minus theta by t is equals to 1 Taylor's expansion. This is e to the power minus x is equals to 1 minus x plus x square minus x cube and so on by 2 factorial by 3 factorial. So this is theta by t square by 2 factorial and so on. Since we know that theta by t is very less than 1, so we can neglect all these quantity after these first two. So this will be 1 minus theta by t. So by putting the value in here, Q vibrational will be e to the power minus theta by 2t divided by 1 minus 1 plus theta by t. So this will be e to the power minus theta by 2t and theta, and this t will go out. So this is the answer at high temperature. Okay, now to the next question. How many are left? Okay, 3-4 more questions only. Vibrational frequency of homonuclear atomic molecule is nu. The temperature at which the population of the first excited state will be half of the ground state is given by. Okay, the population at which the temperature at which the population of first excited state, that is N1 divided by N naught, will be half. Okay, they have given that N1 is half of N naught, so we can write it N naught by half N naught by N naught. This is half. So N1 by N naught is equals to half, that is equals to e to the power minus E1 by kBt divided by e to the power minus E naught by kBt. Okay, so you know that E naught is equals to half h nu and E1 is equals to 3 by 2 h nu. So putting these values here, e to the power minus 3 by 2 h nu by kBt, and here it is e to the power minus half h nu by kBt. So this will become N1 by N naught is equals to e to the power minus h nu by kBt. So we have already taken it as, this is given as half. So e to the power minus h nu by kBt is equals to half. This implies taking log on both sides, h nu by kBt is equal to ln of half. We can write it as h nu by kBt is equals to ln 2. I have removed minus here and I taken this in numerator. So we need to calculate temperature. So temperature is ln 2 into h nu by kb. So ln 2 into h nu by kb. Okay, this one, first one is the answer. The partition function of an one-dimensional oscillator have equispaced energy and spacing is kBt. Zero ground state energy is. The partition function of a one-dimensional equispaced. Okay, this is equispaced, so I think let me check this question again. So h nu by kBt is equal to ln 2. Okay, this t is equals to h nu by kb ln 2. T is equal to h nu by kb, h nu by kb ln 2. So second one, this is the answer. So they have given that ground state energy is 0 and the levels are equispaced as kBt. So we know that q vibrational is equal to e to the power minus theta by 2t for 0 point energy. This is for 0 point energy. Q vibrational is equal to 1 over 1 minus e to the power minus theta by t, that is equal to 1 over 1 minus e to the power minus h nu by kBt. So this is given that h nu is kBt, energy is kBt, 1 over 1 minus kBt by kBt, this is equal to minus 1. So this is 1 over 1 minus e to the power minus 1. We can write it as 1 over 1 minus 1 upon e, taking the LCM, this will be 1 over e minus 1 by e, and this is e upon e minus 1. Q vibrational, E upon E minus 1. So this is the answer. The last two questions only. Vibrational partition function for a molecule with fundamental frequency nu is given by. So this is just a straightforward question. Q vibrational is e to the power minus theta by 2t divided by e to the power minus theta by t 1 minus. Okay. If you put value of theta, this is h nu by 2 kBt divided by 1 minus e to the power minus h nu by kBt. So which one is the answer? This cannot be the answer. This also cannot be the answer. This is for 0 point energy. When 0 point energy E is equal to 0, we can say this is the answer. But when 0 point energy V is not is equal to 0, it is not given here, so we can say that this is the answer. So this is in, okay, this is the answer. This and this are same only. E to the power minus h nu by 2 kBt into inverse of, that is 1 over, then we can write it as 1 over 1 minus e to the power minus h nu by kBt and e to the power exponential of minus h nu by 2 kBt. So now to the next question, and this is the last one. So f is given, this is partition function, and we need to calculate average energy per particle, so U or E, that is equal to n. We need to calculate per particle, so we can remove this n. kBt curl by curl T of Q, ln Q, or F here at constant volume. So ln F is equal to ln A plus ln V plus Bt. From this formula, ln F is equal to this, and taking the differential of it, this will be 0, and this will be 0 at constant volume, and this will be, okay. Now U is equals to kBt into B, so this is B kBt, so B kBt, this is the answer. So thank you, this is all I have for today. So if you have any question, you can ask, and if you don't have any question, you can leave the meeting. Okay, I think I have made a mistake in this question. Here this kBt square is there, so this will be kBt square, this is B kBt square, sorry, this is the answer, second one, because E is equals to, or U is equals to n kBt square curl by curl T of ln Q at constant volume. So this is T square, so I have mistakenly write T here, so this is kBt square B. So B kBt square is the answer. Thank you. You may, if you don't have any doubt, you may leave now.